Okay, in this video I'm going to talk about the strength and stiffness degrading SSD systems compared to those of EPP systems. Okay, so it is a continuation of what we have started in the previous video. So here we have the delta SSD over delta EPP. So it is the ratio between the maximum response obtained from a single degree of freedom system with or using strength and stiffness degradation system or model, and we are comparing it with the maximum response from the same single degree freedom system with using elastic perfectly plastic hysteretic rule. And here, as we have explained in the previous graph, you can see also a similar pattern that you can see here in the horizontal axis. It is the period of the system, which is the period of the single degree freedom system, and in the vertical axis it is the ratio between the two responses, as I have mentioned. In this case we are using it for different ductile systems, starting from response modification factor 1.5 ending with 6. So we're going to find that it covers most of systems, and it is for site classes B, C, and D. So we have 3 different site classes, and we are using mean of 240 ground motions. 240 ground motion. This is the graph that is being used here. As you can see here from the graph, mean ratios of maximum displacement of strength and stiffness degrading system to those of EPP systems, they are shown for different systems, as we said here. Until that we reach almost at 0.8, let's assume that here at 0.8, for example, what you can see here is, here almost it is 1, almost 1. However, before that, there is difference here, big differences. We can reach even to 3.5. What does it mean? It means that the response coming from the single degree freedom system using stiffness and strength degradation hysteretic rule is going to be 3.5 times higher than the same single degree freedom system if we use a EPP or elastic perfectly plastic hysteretic rule. Okay, so this means that before 0.8 and after 0.8 there is a difference that we should put here. Okay, and this is what I put it here as a note. However, in the case of periods shorter than 0.8 seconds, the increase in lateral displacement produced by SSD behavior is larger than that produced by stiffness degradation only. That's right, because stiffness degradation only, the maximum here like 3.5, we were for SSD it is like the maximum 3.5. Let's go to the previous one. Look here, the maximum was 0.8. For stiffness degradation it was almost the maximum 1.8, almost like double. But here we are talking about like the maximum 3.5, so there are a lot of means here. So this means that it is higher, okay, for periods longer, for periods that is longer than 0.8 seconds. After here, the maximum displacement of SSD system is on average equal to that of EPP, and this is right. It is on considered to be the same. Considered to be the same. Okay. Again, this is very good conclusion for us, especially for those who are simplifying their models. If you have a model and you want to simplify it to a single degree of freedom system, and you are not sure which one that or which rule that you should use for conducting nonlinear time history analysis, then this slide is providing you a great deal of, or a very good shortcut for what you should do, which hysteretic rule that you should apply. Okay, if your system, for example, is like higher than 0.8, so this means that no problem, you can use the EPP and this would be okay, elastic perfectly plastic. But if it's less, then the maximum response need to be obtained using the SSD rule. Okay, And this is, as I said, this is the justification of C2, or this is how C2 is working in FEMA and FEMA 356. Okay. It should be noted that displacement ratios shown in this figure, in figure 320, which is this figure for SD, and the other one, which is 321 using SSD, these displacement only correspond to mean, which means average values. So average values means that there is a scatter around the mean. So maybe you are going to find some points, they are higher here or here or something. So we are talking about means values, and that a very large uncertainty exists, particularly for periods smaller than 0.6, and this is very right. Here, like in the short period, whether less than 0.6 or whether less than 0.8, you are going to find that a great deal of uncertainty there. Okay. So this is like the end of this series. I hope that you have understood what these figures are all about. Again, in this short series of videos, I was just trying to explain how FEMA is taking into consideration the effect of different hysteretic models. Okay. So as I said in the beginning of this series, we have like 4 different hysteretic models, and whenever that we are using FEMA displacement coefficient method, we're going to find that we are multiplying the displacement coming from a single degree freedom system by different factors like C2 and so on, right? C2 and C3 and so on. So this C2 is taking into consideration very important concept, which is what is the suitable hysteretic rule that should be used, or what is the hysteretic rule that is governing the single degree freedom system, and what are the differences between them. They took the EPP as a benchmark reference, and then we compare it with other models. We realized that in the case of, or in the different cases, as we have concluded in this video and the previous video, that we are dealing with systems that is, if it's higher than 0.8 seconds, then almost the maximum response is going to be the same, whether from SSD or EBP, EPP or SD. They are going to be the same, because here the previous one also the same at 0.6. We can assume that it's almost 1. Okay, but less than that, you need to be careful. Okay, so the message here is that if you have very stiff systems, you need to conduct nonlinear time history analysis better. Okay, and you need to, in the same time, you need to take into consideration the hysteretic rule that you are going to put. You should be careful with it. And remember that still we are talking about mean values here. There is a great deal of uncertainty already in this part, which is in the short period or periods less than 0.6 or 0.8 seconds. Okay, thank you, and see you in future videos.